I am on page 88, 89. So we started a little bit of page 88 the other day. I did not give you a homework assignment over the 3-day weekend. Sorry, I got 12 emails from your parents saying, am I crazy not giving you guys homework? I'm sorry. Sorry I let you down. All right, so we're talking about independent events. Independent events basically one event has nothing to do with the other, but there's a probability that they both could take place. Independent events could be the same thing taking place. Like we could roll the dice, and each time you roll the dice don't remember what happened last time. Or we could flip a coin. The coin doesn't remember heads came up last or tails came up last. Okay, those are independent events. So those are some things. So a dependent event, one event has to take place in order for the other event to take place. Independent, this event could take place and this event could take place. There's a probability between the two. So a few things that we go with. Hey, thanks, sir. A few things that we have to make sure take place are if I just lost train of thought. I'm sorry. Oh, so there's either, like, if we knew that the probability that we were going to get snow today was, say, 70%, or 0.7, the same thing as 70, and then the probability of snow tomorrow was, say, 90%. The probability that it snows both days, probability both snow, because does the snow that comes today know anything about the snow tomorrow?
Maybe.
It's smart snow if it does. So I'm going to take the probability that it snows the first day times the probability that it snows the second day. If I multiply those together, I get 0.63. So we have a 63% chance that if we had a 70% chance that it snows today and a 90% chance that it snows tomorrow, you have a 63% chance that it would snow on both days. Okay? That basically means if I wanted to do, if it won't snow both days, I can go 100% minus 63%. So I'm going to get 37% that we won't get snow on either of the days, basically. Okay? So that's just kind of a few things on the events. What you have to make sure, in order for it to be an independent event, you have the independent. You have the probability something will happen plus the probability it won't happen has to equal 100% or 1.0, depending upon the thing. So there are definitely things that could happen. You could say, hey, I have a 30% this could take place and a 40% chance that it won't take place. Well, 30 plus 40 is not 100%. So that doesn't mean that would mean they're not independent events. So we were talking about flipping a coin, heads versus tails. You have a 1 in 2 probability of it landing on one side or the other. We do take out the chance that it lands right on its edge. Okay, that would just constitute a rethrow and not count it. But if I wanted to say, hey, I have a coin here, what's the chance I throw a heads, and a heads? I have 1/2 times 1/2 times 1/2, or 1/2 raised to the third power, which becomes, I have a 1 in 8 probability or a 12.5% chance. Okay, probability if I roll a single die, so I get numbers only 1 through 6 coming up. If I wanted to get all 6s, I have a 1 in 6 chance of me on a single die rolling a 6. The probability I roll a 6 3 times in a row is 0.78 or 78% or 0.78 as a decimal raised to the third power. Okay, so there is a chance you could get heads, heads, heads. Okay, it's a pretty lucky throw if you get heads, heads, heads. If there's an 80% chance of rain today and a 40% chance tomorrow, you would just multiply the two decimal amounts about, and there would be a 30, if you had 80% of one day and a 40% the other, the chance that it rains on both days is a 32% chance. So the complement of an event basically means that if I have the probability, if I go 100% minus the event, that's the complement. So if I had a 30% chance of rain today, that means I have a 70% chance that it won't rain. I'm not worried about other weather outcomes, okay? So the complement is just, you're just trying to find the opposite of taking place. So on page 89, they have, you have an event, flipping a coin, you have heads versus tail, rolling a dice, you have an outcome of 6 or 5 or less or something like that. Buying a lottery ticket, you have a winning lottery ticket or a not winning lottery ticket. There's no in between on lottery tickets. The weather this week, 3 or more days of rain, 2 or less days of rain, things like that. Those are just examples of particular events. The probabilities of the two events must add up to 1. So the probability that it will versus the probability that it won't has to be 100% in order for it to fall into the complementary situation, which then goes into independence. Okay? So let's talk about basketball. We have someone in here who plays basketball. He does quite well. I've seen him at free throws, and I like when they're trying to extend the game, they decide to go out and foul this individual who has a pretty good free throw shot, Chambers. Good job on free throws, by the way. So are you the best free throw shooter on the team, or does someone have higher than you? Charlie has higher? So if you are up by 2 with like 15 seconds left in the game, I bet you if there was a timeout called, coach is going to say, get the ball to either you or Charlie, because they're going to try and foul you right away, which means you have a pretty good chance of hitting one or both of the free throws. Agree? And that's a good plan. Now, do you have somebody on the team who's like couldn't hit a free throw if you gave them $1 million? I mean, like someone who's really bad. You don't want the ball to get to it. And guess what? The other team is going to be like, okay, Chambers, what number are you on basketball? 11. So coach is going to say, hey, let's double team 11 on the throw-in, so you would have a lesser chance of them passing the ball to you. The person who has the lower probability of throwing free throws, which that coach, the opposing coach would know, is going to say, we want the ball to go to this bad free throw shooter. Foul him right away, regardless, but we're going to double team the people who are the really good free throw shooters, and we're going to allow the one who isn't quite as good to have the chance to throw. I mean, it's a logical progression, and it's statistics that takes place anytime. And I imagine coach probably tells you the same thing. Let's not let number 3, get the ball. Like if the team is down by 3 and they're going to inbound it, and there's like 1.2 seconds left, you're going to make sure their top free throw shooter doesn't have the opportunity to do that 3. It's like, yeah, inbounded to somebody inside that 3-point thing, so he's going to try and put it up. Don't foul him. Don't get hands on him. Let him take the shot, because chances are the time is going to expire with somebody just putting up a 2 versus a 3. Okay, it's a logical stuff. Statistics takes place. Kind of cool. All right. So Chambers, let's pretend you are an 85% free throw shooter. Okay? So the probability, and this is made up, I don't know if your percentage is this or not, but let's just pretend to go along with the activity. So let's say Chambers has 3 free throws in a game, which I know you'd probably get more, but let's say you have 5 free throws in a game. The probability that Chambers hits all 5 of his free throws is going to be 0.85 raised to the 5th power, or 0.85 times itself 5 times. And that means that Chambers, if that was your free throw, means that you have a 44.4% chance. If you are at the free throw line 5 times with an 85% probability, you have a 44.4% chance of you hitting all 5 of those free throws. Okay? Which is That's reality. Okay? Which means, what's the probability that Chambers would miss all 5 of his free throws? You could do it this way. And the nice thing is you can jump onto our buddy Desmos, and let's clear this out. So the probability that Chambers hits all of his free throws, if he is sent to the line 5 times, is 44%. The probability of Chambers not hitting a free throw is 100% minus 85%, which is 15%. 15% is 0.15. So the probability of Chambers going to the line 5 times and missing all 5 of those free throws is really low. It is 0.0075%. Okay? So there is a very minute chance that a free throw shooter throwing at 85%, hitting 85% of free throws, if they went to the line 5 times, if they missed all of them, is a very low percentage. Okay? Now, let's go into this. Free throw, not. Okay? So this is 5 free throws. Throw up a free throw, and order's not really important. So let's say, what is the probability that at least one is missed? So that takes into account 1 could be missed, 2 could be missed, 3 could be missed, 4 could be missed, or even all 5 could be missed. So what I'm going to do is I'm going to do 100% minus the 44.4%. So the probability that a free throw shooter who is shooting 85% of the free throws at the line, the probability they miss at least 1, so again, they can miss 1 or 2 or 3 or 4 or 5 if they went 5 times, there is a 55.6% chance that one of those free throws or more is missed during the game. And again, you don't want to worry about order on this, okay? Things that you want to look at when you're talking about complement of a problem. Look for phrases saying that suggest many possible outcomes, like, at least, at most, greater than, less than. Those are all going to take place in this type of event. Okay, so you just want to keep an eye on those kind of things. I want to give you the opportunity to work on the assignment. We have an awful lot of time to get it up and going. Do I think there's a snow day going to happen tomorrow? Yes. Stirrup, you jinxed it. I know. Because Stirrup's voice has something to do with the weather. All right. I'll take a snow day, though. But I'd like you, next time we would have class, I'm going to have page 203 and page 204 due. Okay? Next time we have class, whether it's tomorrow, if we don't have a snow day or a delayed start, or if we have a snow day, then on Thursday. Cool?